So like I said, we are going to use this particular GPS unit. It is the Adafruit Ultimate GPS Logger Shield. That's the piece of hardware that we're going to use. So we talked about it. We went over the GPS system. And like I said, this is the actual GPS unit we're going to use. It has a couple of different capabilities, not just GPS. And we're just going to go over like what are the major components on this little circuit board. So if we zoom in and look at it from the top, here's the big components, right? So obviously it has a, or not obviously, like I said, it has a spot for an SD card. So you have a slot where you can actually put in the micro SD card. It has this little connector, and what that's for is connecting an external GPS antenna. This brown ceramic piece here is the actual GPS unit with the built-in antenna on top. That's what the piece of ceramic on top of it is. It has a spot for a battery coin cell, right? That's just a little flat battery that slides in here and provides this thing backup power. And then the other big thing that it has is it has this prototyping area. So it has basically a small proto shield built into it. But none of these individual pads are connected to each other. So if you want to make connections, you basically have to have wire going from spot to spot and solder it in. So if we zoom in on those different components, so this is that antenna connection. It is very small. The particular type of connection that's called is a UFL connection. The most common antenna connection type is called something called an SMA connector that is not this. So you can't, most GPS antennas that you can buy, you're going to have an adapter to connect it to this. They made this, they use this style of connector basically to keep it small. So most of the time, you don't need an external connection antenna. But if I'm using some shielding or a metal, if I have like a metal payload mechanical construction, that and my GPS unit was inside of that, that metal would block the GPS signal. So I would basically need to use an external antenna so that I could just put the antenna out on the outside of my payload. That's typically what those are used for. Also, it could be that maybe there's something close to my antenna and the rest of my electronics that's interfering. So I want to put my antenna far from that source. The actual GPS unit here is going to basically automatically tell when an antenna is plugged in there, and it should switch over. And there are particular sentences that will tell you the status of the antenna. It'll tell you if it's on an external antenna or the internal antenna, and it will also, or if there's some sort of error. But usually you don't need that information because we're not really going to use an external antenna. So you don't usually need to use it. The point of the coin cell is to keep the backup power memory to the GPS. And that's because the GPS includes a real-time clock. So when the GPS gets an accurate satellite fix, it will set that clock. it'll say, oh, I know what time it is. It's this time now. If you have the coin cell installed, if the GPS loses power, i.e. like you turn it off, but the coin cell is still in, so it has backup power, that will keep the clock basically counting and it'll have the correct time when it starts back up. But it doesn't have a built-in battery as part of the unit, so that's why you have this coin cell where you have to install a little external battery. It doesn't use a lot of power to keep that clock running while it's off. So you should be able to use the little coin cell for several years before you have to replace it. The other thing that using that coin cell does is it lets you do something called a hot start. So normally when the GPS starts up, it does something called a cold start. It has no idea what time it is down to the year. It defaults to like January 1st, midnight 1970. And it has no idea where it is on Earth. So because of that, it has no idea which satellites it should be able to see. So it's just going to have to start checking through and see which satellites it can see. Basically scan for all of them. And that's going to make it take a relatively long amount of time. Usually, like, I believe the spec is around 30 seconds to get a fix. Once it gets the fix, it knows its position and it knows its time. So if you have the coin cell installed and the GPS gets shut down and started back up, it will keep in memory because the coin cell will give it power to let it know what was its last position and its time. So now it knows which satellites it should be able to see, and it'll be able to find a fix more quickly. And that's called a hot start. So that will take like 5 seconds as opposed to like 30 seconds. You also have 3 LEDs that indicate a few different statuses. So you have this green power LED. And that's just solid on if the thing has power. If that LED is not lit, that means there's something wrong with your shield. It's not plugged in correctly. You're not giving it electricity. This middle LED is connected to pin 13. And it's basically connected to the pin that is the data line going to the SD card. So when you are writing data, when you are talking to the SD card, that thing will flash. And then the final LED is labeled fix. And as you can imagine, that tells you if it has a fix or not. I'm not quite sure why they just didn't make it on or off. But what it'll do is it'll basically blink once a second. So on, off, on, off. And that means the GPS does not have a fix. If it starts to blink more slowly, where it's basically off, and then every 15 seconds turns on, that's when it has a fix. So those are the 2 sorts of behavior you should see about the out of the fix LED. Prototyping area is fairly straightforward. It's just a bunch of circular solder pads where you can install your own electronics components and solder them onto the board. So you can use this to build little simple small circuits without having to have an entire proto shield or something else. You also have this small breakout area to the right here with a few connection points labeled. And that's so that you can actually connect to these other other pins for your own use. So there is a label called 3 volts or 3V, and that's a 3.3 volt. Because the GPS and the SD card actually operate on 3.3 volts, the chip that is right here is actually one of those level shifters we talked about. And because of that, that means it needs to generate and have 3.3 volts. So if you needed a source of 3.3 volts, you could use that. You're most likely not going to need it. There is this CD pin, and that's part of the SD card. Basically, when there is no SD card installed, that will be connected to ground. And when there is an SD card installed, like and by installed we mean physically inserted in the slot, it won't be shorted to ground. So that basically, by looking at the signal on that pin, you can tell if there is a SD card actually in or not. This is a CCS, or this next one is labeled CCS, and that is a chip select pin. So if you remember when we talked about SPI protocol, you need a chip select pin. And the way you actually talk to the SD card is through SPI protocol, which means the SD card needs a chip select. So that is connected to the chip select of the SD card. And on the Arduino side, it's connected to, by default, to pin 10. But because they have this little breakout area, you could install a wire here and connect it to a different pin. There's this pin called PPS, which stands for pulse per second. So one thing that a GPS does is it will give you a very, very accurate pulse that is occurring at the top of every second. And when that pulse starts is accurate down to several microseconds or nanoseconds, depending on the component. But what that lets you do, that's how you really want to do synchronization, because if you look for the start of that pulse, you can see very accurately. Whereas if you're trying to read the clock, you actually have to worry about the time it takes to transmit the characters, which could take microseconds or milliseconds. And then you have the TX and RX pins. So the way that we are actually going to talk to the GPS is through the serial. So it uses a UART, so it has a TX and RX line. So it transmits data on the transmit line, and you will send it commands on the receive line. So one other thing is there is this little switch here labeled soft serial or direct. So what that does is it selects which of the pins the GPS is connected to. When it is in the direct position, the GPS is connected to pins 0 and 1, the TX and RX 0, right? But that has a bit of an issue because those are the pins that we use to monitor the serial monitor. That's also the pins that we actually transmit our sketches on when we upload code to the Arduino. What that means is you cannot actually upload code when the GPS is installed and the switch is in the direct position, because the GPS will just be spitting out data, and that'll interfere. So your computer will see that on the USB port, and it won't know what that is while it's trying to transmit code, right? Because there's acknowledgments that happen when you transmit the code, and if the GPS is just spamming data on that same line, it's going to interfere with it. What that does let you do, though, is you can basically have the GPS in that switch in that position, connect the USB port, and open up the serial monitor, and you will be able to see the data that the GPS is spitting out, because it's just character strings. And if the Arduino isn't doing anything, so we usually want to upload a blank sketch before we do that, which is just a sketch where the Arduino does absolutely nothing. And then we plug in the GPS shield, switch it to direct. We can actually see the data it's spitting out. And we can also type in commands directly through the serial monitor and send them directly to the GPS. But that's when we're using our computer. So when we're actually interfacing the GPS with the Arduino, we want to set it up differently. So for that, we want the position in the software serial, the switch in the software serial, which is here. It says soft serial. And that is going to connect it to pins 7 and 8. Well, it's going to connect it to this TX and RX right here, which are directly wired to pins 7 and 8. And what that'll let us do is we're going to install a jumper on these two pins, and we're going to connect that to the other serial ports, right? So on the Mega, we have serial 0, and we have serial 1, 2, and 3. The reason that's called software serial is, like I said, that layout was based on an Arduino Uno, which only has a single serial port. So if you were not going to connect to pin 0 and 1, you would have to do a software serial, because pin 0 and 1 is the only hardware serial on an Uno. But because we have those extra pins, or those extra hardware serials, we're going to install wires such that we can just connect to one of those other ones. And that's going to let us use serial 0 to talk to the Arduino, and the other serials to talk to the GPS. So this is, again, just restating that when it's in this position, you're basically connecting the GPS to the USB port, which is going to mess up when I try and upload sketches, but I can actually look and directly see what the GPS is doing and send commands directly to it. And then again, in the other position, I can connect to these. I can use a jumper to connect to the other ones. So that's what this is. In this picture, we've soldered a connection on there, and I've got this yellow and orange wire, and it's going to, I think that's serial 2 right there. But the point is I could then move this to serial 1 or serial 3. And what that allows me to do is have one serial port dedicated for the computer communications and use the GPS on the other ones. So that is it for the actual GPS Shield hardware.